transformation and a very important property, namely the eigenvalues and eigenvectors of a linear transformation. Now, this is one more important thing that we want to now relate to linear transformations. So, it's what is called the matrix. Recall what matrix so far we have been studying is just a rectangular array of elements or a box of elements, so arranged in rows and columns with certain properties. Now it's time to get away from this box definition, and a proper mathematical definition of matrix should be put forward. So for this matrix of a linear transformation, therefore we want to discuss. So now let us take that V over F be a vector space, and this B of dimensions n finite, and T be a linear transformation on V. Then suppose we have a basis because the dimension is n. Further, let there be a basis V1, V2, and say Vn be a basis for the vector space V over F. Now, let us observe that every vector V in V is a linear combination of the basis vectors. So, for every V in V, there exist uniquely determined scalars. There exist uniquely determined scalars alpha 1, alpha 2, say, let us say alpha n in F, such that V is a linear combination. So alpha 1 V1 plus alpha 2 V2 and so on, alpha n Vn. Because V1, V2, Vn is a basis. Now T is a linear transformation. So it is a map from V to V. It takes V and the element under T is the image of V under T. This is Vt. Now this is also here in V. So in particular for Vt, the same thing will happen here. That this is again in the linear span of D, and therefore is a linear combination of these basis vectors. So this again, so this V is naturally the linear span of B because B is a basis. So Vt is vector in V, and therefore for this Vt also we can write this as, so this will be again a linear combination of V1, V2, Vn. Now in particular if you look at the basis vectors, so say Vi, so Vi will go to Vit. This is here in V, and therefore in the linear span of B, and therefore this Vt can be written as a linear combination of V1, V2, Vn. Now corresponding to each I, since we are doing, and therefore we shall write this as alpha I1 V1 plus alpha I2 V2 plus alpha I n Vn. Now this is for every I. This is for every I 1 to n. So what we are getting here for I is equal to 1 alpha 1 1 V1 plus alpha 1 2 V2 plus alpha 1 n Vn. So I is equal to 2 Vi becomes V2. So V2T will be a linear combination alpha 2 1 V1 plus alpha 2 2 V2 plus alpha 2 1 Vn, and the last one like that. When I becomes n, this will be V and T as the linear combination alpha n1 V1 plus alpha n2 V2 plus and so on alpha n Vn. So what we observe therefore is that we shall have this sort of thing. So V1 T will be alpha 1 1 V1, alpha 1 2 V2, and this will be, say here, alpha 1 J this is alpha 1 J B J and so on, alpha 1 N B N. Like that, V2T will be alpha 2 corresponding to this 1 V1 plus alpha 2 2 V2 alpha 2 J Vj, and this will be alpha 2 N Vn. Like that, Vi T for arbitrary I between 1 to n. This will be alpha I1 V1, alpha I2 V2, alpha I J Vj, and alpha I n Vn. And like that, the last term will be Vn T alpha n1 V1, alpha n2 V2, alpha n J Vj, alpha n n Vn. Where these alpha ij's are naturally uniquely determined scalars from F, and I and J both are between 1 to n. So if you want, we can write the whole system of equations. So this can be written as writing VIT. So VIT is this, and this can be written as alpha ij Vj, J is 1 to n, and this is for every I 1 to up to n. Now, just so there are alpha ij's if you see. So I takes values 1 to n, J also takes values 1. So these are uniquely determined scalars, and they are in number n square. And as I said, that to know any linear transformation, that means to know Vt, it is enough to know Vit for every basis vector. This is a phenomenon. And therefore, these uniquely determined linear combinations will completely determine T, these scalars alpha ij in F. So what we do is that the matrix of T, so the matrix of T with respect to this basis B is often written as TB. So just retain these scalars because V1, V2, Vn we know, and we also know that in which order these all are written. So this is alpha 1, 1, alpha 1, 2, and then alpha 1 j, and then like this alpha 1 n. Like this alpha I1, alpha I2, and this is alpha ij, alpha in, and like that alpha n1, alpha n2, alpha nj, and alpha nn. Now, if you look at the number of rows is n and number of columns also n. This also is very common to write arbitrary element which is here in the ith row and in the jth column. This is jth column. And the intersection is this arbitrary element alpha ij. So this is also pretty common to write this just this alpha ij to denote that this is the element at the intersection of ith row and jth column, and the number of rows specified so that the range of I is known, and likewise number of columns also specified. This is j that it takes 1 to n. So j number of columns are also specified. Now this is called the matrix here of T with respect to the basis T. So we shall have some simple examples, and then we shall see that there is a one-to-one correspondence between a linear transformation and its matrix with respect to a basis. So first, some examples. So let me take the simple example. So the simplest example is the identity linear transformation as we had seen here. Okay, so let us take that the dimension of the vector space be. So let us take this again. It's better to take a small example. So say R2 R2 over R. Let us take this B. Then the dimension of this V over F is 2, naturally finite. And T is the linear transformation V to V. V goes to Vt, and Vt is, let us say, V itself for everything. So this is the identity linear transformation, and so let us define this also by this. So say I. Now a basis for R2 over R, let us take this is this. Say here. So V1 is say 1, 0, and V2 say 0, 1. With the standard basis for V over F. Then to write the matrix of I with respect to the basis B, we need to know Vi under I for I wanted. Now what we know is so V1 of I is V1. This we can write as the linear combination 1 V1 plus 0 V2 as the linear combination of V1 and V2. Similarly, for V2 under I is V2. Therefore, this is your 0 V1 plus 1 V2. So when you write this as the matrix alpha 1 1, this is alpha 1 1 V1, alpha 1 2 V2, alpha 2 1 V1 plus alpha 2 2 V2. So what we see here is that alpha 1 1 is alpha 1 1 is 1, alpha 1 2 is 0, alpha 2 1 is 0, alpha 2 2 is 1. And the matrix of this with respect to the basis B is alpha 1 1 is 1, alpha 1 2 is 0, alpha 2 1 is 0, alpha 2 2 is 1. This is 2 by 2, 2 rows, 2 columns, and the entries are 1 0 0. Nice. So example 2 now let us see. Again same, V R2 over R, and identity is the linear transformation here. So V to V, V goes to VI, VI is V only, and let us take this B prime as another basis. W1, W1 is 0 1, W2 is say 1 0. So observe that the basis is same. B prime and B are same sets. And the are same sets. So we want to know what is the matrix of I with respect to the basis B prime. And therefore, once again, we want to know what is W1 under I, this is W1. So W1 is 0 1, 0 1. Same here. And so this you can write as the linear combination. So this is W2I is W2. So 1 W1, 0 W2, 0 W1, 1 W2. So the matrix of this with respect to B prime is 1 0 0 1. If you look carefully, then W1 is V2. Also observe that this W1 V2, W2 is V1. So if you see here and if you write this as the linear combination in terms of V1 and V2, then this W1 will become V2 So this will be in terms of, if you want to see, so this is 1 V2 and 0 V1. So this will be 0 V1, this 1 V2, and this will be 1 V2 plus 0 1. So with respect to the linear combination, if you write for the image, then this will be the linear combination. We shall see what happens when we change the basis in next few examples. Another example that we had yesterday discussed was a simple example where the linear transformation on R2 over R was given. We also had the example, by the way, alpha I. Example 3 was of so V again alpha I on say V is R2 over R V, and V goes to alpha I of V. So this is simply alpha of Vi, alpha of Vi, alpha V. And the matrix with respect to the basis as again standard basis, let us say 1 0, V2 say 0 1, then the matrix of alpha I respect to the basis B, this becomes simply alpha 0 0 alpha. So this is for you to verify. So this is again a 2 by 2 matrix. Another simple example, let us take that T be the linear transformation here. V is R2 over R 2V, and say V is X Y going to VT, and VT is X plus Y. All right. So let us again take the standard basis as the basis for this, and let us take V1 as 1 0, V2 as 0 1. So in that case, 0. So V1T. So to know the matrix of T with respect to the standard basis B, what we need to know? V1T into T. Now V1T. V1T means 1 0 under T. So this is 1 plus 0 and 0. So this is 1 0. 1 0 is V1 only. Linear combination 1 V1 0 8. V2 T. V2 is 0 1 T. So this is 0 plus 1 and 1. So this is 1 1. And when you write this 1 1, so this can be written as 1 0 plus 0 1. And this can be further written as V1 plus V2. And that makes 1 V1 plus 1 V2. So what we get here is as the matrix of T with respect to the standard basis B is this. So it's the 1 0 and then 1 1 1 1. So this is the with respect to the standard. basis. Another example, let us take the same linear transformation. Example 5, same linear transformation, say T V R2 over R to V goes to Vt, and if it is xy, then this xyt, x plus yy. Now let us take another basis here, say W1 is say 1, 0, and W2, let's say 1, 1. You can verify that this also is a basis for V over F. Now we want to write the matrix of this T with respect to the basis B prime, and therefore we need T as we had seen earlier also, so is 1 plus 0 and then 0. So this is 1, 0, this is again W1. The linear combination is 1 W1 plus 0 W2. That will give the first row of the matrix. W2T will be, so this is 1, 1, T. 1, 1, T is 1 plus 1 and then 1. So this is 2, 1. So this is same as 2, 0 plus 0, 1. This is further 2, 1, 0 plus this is here 0, 1. So this is actually, sorry, we need to express in terms of W1 and W2. So this has to be a little changed. 2, 1. So after that, this is okay. So this is 1, 0 plus 1, 1. So it's so it's 1, 0 plus 1, 1. So this is W1, W2, and this is what it gives, that the matrix of T with respect to the ordered basis B prime is 1, 0 and then 1, 1. If we take another example 6, same linear transformation V R2 over R, V goes to Vt, xy goes to xyt, x plus yy, and B double prime, let us take is here U1 is here say 1, 0, and U2 is say 0, 1. Then U1T is, as we had seen, is U1. So this is 1 U1 plus 0 U2. And then U2T. U2T is 0, 1T. Sorry, should interchange actually. Let me interchange for this is interchange. Let us take this to be 0, 1. And this is as 1, 0. Okay, so this becomes 1, 1. U1T becomes 1, 1. So this becomes 1 1. This becomes 1 1, and this is 0 1 plus 1 0, and this is your u1 plus u to t. So this is 1 0, which is u1, and this is now u2. U2 is 0 u1. The matrix of t with respect to prime is 1 1 0 1. So this is a different matrix that we have got this time. Although we have that this set wise this B prime, double prime, and B are same, but still the matrix are different. Two matrices are said to be equal if and only if they have same number of rows, same number of columns, and each corresponding entry is also equal. So this we have got a different matrix, that TB prime is not actually TB. Let us go for a little more sample, one more example. Say example 7. It's a little bigger example. So let us take V to be the vector space here, FBA field, and let us take V to be, say, the vector space Fx, consisting of all polynomials of degree at most. So this at most say 3. So in that case, let me put this at 3. No, this will not be proper to put here. Let us put it here. So this consists of polynomials here in x over f, and the degree of fx is less or equal to 3. And this is a vector space, and you can see that its dimension is 4, and you can take b as a basis, as a b1, the basis, say v1 is 1, v2 is x, v3 is x square, and v4 as x cube. Now this is called the standard basis. So standard basis for v3 over f. Now we want to write the matrix of a linear transformation over this. So first of all, a linear transformation. So let us take D. We defined V to V. Elements of V are polynomials, say fx, and define this as fx d. Fx d is the derivative d by dx of fx. So if fx is say for example here, So if fx is a0 plus a1x plus a2x squared plus a3x3, then this image here, fx and d, the derivative of this, so is a1 plus twice a2x plus 3a3x squared. So I want to write the matrix of this d with respect to this basis. Now to write the matrix of this with respect to this basis, what do I have to do? Is I have to express what is V1D, V2D, V3D, and therefore let me write now these expressions. So V1D is here. So is the derivative of A0, and this is simply 0. So this is 0 V1 plus 0 V2 plus 0 V3 plus 0 V4. V2D. V2D is the derivative of here V2 is x. This is 1, and this can be written as, so 1 V1, 0 V2 plus 0 V3 plus 0 V4. V3D. V3D is the derivative of x squared. This is twice x. Twice x is 2v2. So this is 0 v1 plus 2v2 plus 0 v3 plus 0 v4. And finally v4d is the derivative here of x cubed. This is 3x squared. So this is 3 and x squared is v3, so 3v3. So this is 0 v1, 0 v2 plus 3v3 plus 0 v4. So if I have to write the matrix of D with respect to this basis, let us say B1, then what I do get here? So the matrix of D with respect to the basis B1, then I get here. So there are 4 rows and 4 columns, so order 4 by 4. And you can see the first row is 0, 0, 0, 0. The second will become 1, 0, 0, 0. Second will become 1, 0, 0, 0. And the third will come from this. So 0, 2, 0, 2, 0, 0. Third will come from the next, that is fourth. Fourth will come from the last equation. So this is 0, 0. This is 3 and then 0. So this is what is the matrix of this. 1 second. me rewrite this once again. So what we have got is here. So we saw the vector space of all polynomials of degree at most 3, and V1 was the basis. V1 as 1, V2 as x, V3 x square, V4 as x cube, and the matrix of D with respect to V1 we have got is, so it's 0, 0, 0, 0, and then 1, 0, 0, 0, 0, 2, 0, 0, and 0, 0, 3, 0. This was the matrix that we got. So the next example 8, let us take the same as the vector space here. So let us take V3 itself is the vector space. So V3, this is the set of all polynomials fx and fx, and degree of fx is less or equal to 3, and let us take this times another basis b2. Let us take this basis b to be the basis, say for example, if you just write, let us take W1, if you write in the reverse order, so this is say x cube, W2 is say x square, W3 as x, and W4 as 1. So you can observe that set-wise, B1 and B2 are same. So we want to write dV2. So to write dV2, therefore, we need to know what is the image of each basis vector under D. Now W1D. W1D is the derivative of this 3x square. 3x square is now 3W2. This is therefore 0W1. Sorry, this is 3W2, 0W3, and 0W4. W2D is the derivative now here of W2 is x square, so this is twice x, and this is twice x. X is W3, so 2W3. So 0W1, 0W2 plus 2W3 plus 0W4. And now you have here W3D, the derivative of x. This is 1. 1 is simply W4. So that makes this is 0W1 plus 0W2 plus 0W3 plus 1W4. And W4D is the derivative here of 1, and is 0. And that makes that W4D as the linear combination 0W1, 0W2, 0W3, 0W4. So this gives me the matrix here. So dV, dV2, therefore, is again 4 rows, 4 columns. And you have here, so its first row is here your so 0, 3, 0, 0, 0, 3, and 0, 0. Second row is from here, so 0, 0, 2, 0, 0, 0, 2, 0. Third row will be 0, 0, and this is 0, and this bottom row, fourth row will be all entries 0. So this is 4 by 4. So you can see once again that if you compare each element in these two matrices, they are not same. You can take that way different bases and can see what is happening here. Say for example, if you take one more basis, say B3, example 9. Same vector space is V as V3. V3 is a set of all polynomials here. Degree of fx is 3. And again, dv to v is so fx going to fx under d, the derivative of fx with respect to x. And let us take u1, the basis b3, basis b3. You can check that this also is a basis. u1 is takes a 1, u2 1 plus x, u3 is say 1 plus x square, and u4 is say 1 plus x cubed. And you want to write the matrix of D with respect to the basis B3. So once again, so u1D is 0, and therefore this is 0 u1, 0 u2, and 0 u3 plus 0 u4. u2d is the derivative of this 1 plus x. So this is 1 and this is u1. So u1 is simply, so is 1 u1 plus 0 u2 plus 0 u3, 0 u4. u3d is the derivative of 1 plus x squared. This is twice x. Now twice x, so you can see that this is 2 into 1 plus x. So this is 2u2 minus 2u1. So this is twice u2 minus u1. u2 minus u1. So this is minus 2u1 plus 2u2 and 0 u3 plus 0 u4. And you can also take now as u4d. So u4d is the derivative of 1 plus x cubed, the x square. Now x square comes, so here, so if you subtract u3 minus u1, then this is x square. So this is 3 u3 minus u1 minus 3 u1, 0 u2 and plus 3 u3 plus 0 u4. So the matrix of D with respect to this basis B3 is same as obtained from here 4 by 4, and first row will come from the first equation, so all entries will be 0 0 0. The second is 1 0 0 0. Third will be minus 2 minus 3 0 3 0. So this will be last fourth equation. So like that, we have got plenty of examples for the linear transformations and their matrices. So, almost 9 o'clock. That won't give us much time to do something new. But yes, one thing you can still see with respect to this example. Let us come back to the problem that we had seen already with eigenvalues, eigenvectors, and so on. And take this to be the D to be the linear transformation, and find out the eigenvalues and eigenvectors for D. So, for example, if I just take the case same vector space V. So this is the set of all here polynomials. Fx in fx and degree is fx lesser or equal to 3. And you have the same linear transformation D, V to V, fx going to fx of D as the derivative of fx. And if you want to find out the characteristic roots of this is finally find the characteristic roots of B. F here, let us take B F, F B, let us take R, real polynomials. So if lambda in F is a characteristic root of D, then there exists a non-zero vector V. V means fx. Fx is here a0, a1x, a2x square plus a3x cube as the basis. So if you take the standard basis B, and the basis is let us take B1. B1 is the standard basis. V1 as 1, V2 as x, V3 is x square, V4 is x cube. So lambda, so then such that Vt is equal to lambda V. So that means Vt is here fx. D is equal to lambda fx. That means d over dx of fx is lambda fx. And if this is the expression here for fx, then the derivative will be a1 plus twice a2x plus 3 a3x square. This will be the derivation here of fx with respect to x. So this is lambda a0 plus a1x a2x square plus a3x cube. You can write this as a linear combination of the basis vectors. So this is same as, so what is the coefficient of 1? So lambda a0 minus a1. Lambda a0 minus a1 plus the coefficient of x. So this is 1. The coefficient of x will be lambda a1 minus here coefficient of x 2a2. So this is 2a2x. Then coefficient of x square lambda a2 minus coefficient 3a3. 3a3 x square. Finally, x cube, so there is nothing. So this is a3 x cube multiplied by lambda. This is 0. So this is your linear combination of the basis vectors. This being 0 means each coefficient has to be 0 because basis vectors are linearly independent. So what you get is that lambda a3 is 0. If you write this, gives you lambda a3 is 0. And all other coefficients also 0. Lambda a2 is minus 3a3 is 0. Lambda a1 minus 2a2 is 0. Lambda a0 minus 1 is 0. So you get a system of equations in a0, a1, a2, a3. Now it will depend on what is your polynomial. So if a3 is not 0, then lambda will be 0. Because we are in a field, so either of the two are 0. So if the a3 is not 0, in that case lambda will be 0. And if a3 is 0, then lambda can be anything. So I leave for you to find out here what are the eigenvalues of B. So find out these values of lambda. What you are using is that B is non-zero. B is non-zero means not all coefficients a0, a1, a2, a3 are 0 at the same time. And you will enjoy the problem. So next time when we meet, then we shall talk about the relationship of the matrices that we obtain of a linear transformation with various bases. Examples we had already seen, but what could be the relationship between these two? That we have to see that what happens when we change the bases. So thank you very much for your kind attention.
Thank you, sir.